Okay, my dear friends, good afternoon. Welcome back to the calculus series of proud product of Bursity Academy. Today, our focus gonna be mainly centered on not the area under the curve. So far, last few weeks, we've been talking about how the integration can be applied in the day-to-day life. Now today, integration has another application. It's a kind of like extension of what we've been doing earlier. In this application, you can remember, if you can recall very clearly, and just get that in front of you, that the clear picture that how we've been describing that one time, that area under the curve using the integration, the area under the curve. Today, what we're going to do, instead of having a one curve, we're going to have two curves, and then we're going to see the area entrapped between, not under, area entrapped between these two curves for a given certain interval or certain domain or certain region. For this one, heavily utilized in practical application, because there are two kind of a situation. Sometimes you're going to talk about, especially in economics or econometrics, profit or your cost or your revenue, mainly the cost and revenue, and can be drawn, those two curves can be drawn. Revenue, which is denoted by R of X, X stands for the number of items being sold or bought. It depends on from the perspective of seller or buyer. And cost, which is denoted by C of X, here same thing, that number of items being manufactured or number of items being sold, number of items being bought, or anything in any kind of a scenario. These two curves can be drawn on the same axis system, Cartesian axis system. Once you draw these two, we really want to find the difference between the cost and the revenue, which is referred to as the profit or losses. These profit and losses, if you're going to take over a certain interval, that's where we have to find the area entrapped between those two curves. That's one of the example. Except for this one, in addition to this one, there are so many examples being put forward into mathematical and economical and statistical arena. To make this discussion very fruitful and very advantageous for the student who are taking calculus whole series, Calc 1, Calc 2, Calc 3, maybe Calc 4, and then you're going to jump into the differential equation, first order differential equation, second order differential equation, then partial differential equation. Eventually, unfortunately, at the end of the day, that what's going to happen, that pretty much math will be overshadowed by statistics. What's going to happen in like a LCR circuit, if you're going to measure the voltages across all three components, inductor, capacitance, and resistor, those three components, and if you measure that one practically, eventually this all these three components being connected by a certain battery, when you're going to measure those practically, there would be an error. That error can be neglected. Error will be taken into account at the end of the day in order to come up with the exact solution for our problem. To get the exact solution, that error term, it's not a fixed thing. If you're going to measure that one again, that error would not be the same as the first error. Because of the errors, this anomalous behavior, or this kind of like a different kind of a behavior, this automatically becomes a random variable. The very moment that error becomes a random variable, that would constitute a certain distribution that can be modeled with any kind of a distribution that's been put forward into statistical arena. But for our mathematical tractability and easiness, what we're going to do in the first place, that kind of an error will be modeled with the normal distribution, which is bell-shaped and symmetric. So bell-shape has been even named after the great mathematician Carl Gauss, who invented this one. That's why we're going to call that one sometimes a Gaussian distribution. So those kind of scenarios, we're going to take into account down the road, one by one. But for time being, if I'm going to go back to my original discussion where I started and say that I'm planning to have planning to find the area intercept between two curves, to support this discussion, I would like to cite an example and work through that one step by step for your convenience, for your comprehension, for your digestion, and then eventually you're going to be an expert on how to find the area intercept between two curves. Let's look at this example. Let's look at this example. Example. Find the area between, this is how I'm going to write between, you are now familiarized with my abbreviations, between area of the region, between area of the region intercept between the, this is between, abbreviated as, see, this way, between the graphs of functions, I'm going to write functions in this abbreviation, f of x equals x squared minus 4x plus 10, and g of x is nothing but 4x minus x squared. 4x minus x squared over the interval 1 to 3. See, this interval. The endpoints are included. That's why I'm using the bracket instead of using the parentheses. If the parentheses were thrown over there, then that means the endpoints are not included. This is a question. Find the area of the region between, find the area entrapped between the graph of these two curves. The two curves which are modeled, which being modeled by f of x, x squared minus 4x plus 10, x squared minus 4x plus 10, and g of x, 4x minus x squared over certain interval. That interval is 1 to 3. That's the question. How could we going to get this done? What's the first and foremost thing to be done in order to find the area entrapped between these two curves? First thing, we have to draw two curves. Even before we're going to draw the two curves, you have to find one particular thing, one very special characteristics between these two. That would be the points of intersection. We have to see whether these two graphs of these two functions going to meet each other. To get this done, what would be the mathematical implication? How could you going to do this one mathematically? To get this done mathematically, you have to set f of x equals to g of x, assuming that at the points of intersection, the y coordinates, the heights of the y coordinates are the same. Let's get this done. Let's try to find the points of intersection. First, by finding points of intersection, which is abbreviated as points of intersection, POI. Excuse me, by matching f of x and gx, we can find the points of intersections. Points of intersections. That is, f of x equals g of x. See? That is x squared minus 4x. F of x is nothing but x squared minus 4x plus 10. Gx is nothing but 4x minus x squared. See? See? This is how mathematically we're going to find the points of intersection. Look at now. This looks like a quadratic equation. If it looks like a quadratic, means like a second order. See, the order is 2. The highest order is 2. The highest degree is 2. The highest power is 2. The highest index is 2. You can explain that one in any way you want. You're going to explain same thing in different forms. So x squared minus 4x plus 10 equals 4x minus x squared looks like a quadratic equation. If it is a quadratic equation, in order to solve this one and come up with the solution at the end of the day, you pretty much have to get all the terms to one side. Let's get all the terms to one side. I prefer to get all the terms to my left hand side, to this side. So I have x squared minus plus, because I'm going to bring this one to this side, x squared. I already had minus 4x here. I'm going to bring this 4x to the other side. That also become minus 4x. Plus, I already had 10 equals 0. See? So you got left over with just simply 0 on the right hand side. See? Now, let's combine these two. This is nothing but 2x squared. You have 2f then. This is these two nothing but 8x. The last term go by itself or standalone, that would be 10. See, you are left over with very nice quadratic equation. But still we are not done. Looks like there's something common to all these terms. We have 3 terms, 1, 2, 3. So 2 would be common term. So you can just divide through by the equation by 2. Then you're going to get x squared here. When you divide 8x, you get 4x here. When you divide 10, you get 5 here. You see? See? You came up with a very nice quadratic equation with 3 terms, x squared minus 4x plus 5. Now, what are you going to do? How do you solve the quadratic equation? There are 4 ways you can get this done. There are 4 ways you can solve the quadratic equation. Graphical, using graph. That means using drawing this graph and this graph. Y equals 0. Y equals 0 is nothing but x-axis. And this graph, this represents what? Once you draw this one, this represents a parabolic shape. Parabolic shape. And by looking at the sign of the x squared, or the leading terms or leading coefficient sign, you can figure out whether you're going to have a open upward or open downward. In another way, whether you're going to have a minimum or maximum for this graph. By looking at this one, you see that this is positive. If it's positive, it looks like it's a minimum. It has a minimum, it would open upward. But that's the one way of solving that equation. The second method, factorization. By factoring this term, you can easily get a solution. The third method, using the quadratic equation. And the fourth one, completing square. Out of all these 4 methods, I think, from my point of view, from my perspectives, I think the factor method would be far easier. But sometimes you can use the graphing calculator and get this done using the formula or any kind. Anyhow, that's not the case over here. So mathematically, if you want to do something over here, let's say where we are planning to use the factor method, as I suggested earlier, factor method. This say that you're going to add. This say that negatively add. Who would be negatively added? The factors of 5. 5 can be split into only 2. split into 2. Which way? 5 times 1 or 1 times 5. Once you add those two, would that make the middle term? No, see, looks like this is non-factorable. Non-factorable. See, you're gonna split this guy, x and x, that x squared. See, you split x squared, the first term. You're gonna split the last term, 5, which is 5 times 1, and then you take the cross multiplication. Here x, here 5x. This sign say add. If you add, how you gonna add? Negative, negative. That would not give you the middle term. That would give you minus 6x. That's not what we have over here. In that sense, this is non-factorable. Non-factorable. But we're not going to give up. We still have a hope, because still we have 3 more methods to be utilized in order to find the solution. We were thinking about using the quadratic formula. In the quadratic formula, before we go to the quadratic formula, we can figure out whether we have a solutions or not by looking at just the discriminant, some part called, can you remember the quadratic formula? If the quadratic equation has been given in ax squared plus bx plus c form, see, if ax squared plus bx plus c, you can remember x can be evaluated by minus b plus or minus square root b squared minus 4ac divided by 2a. But there's a part called b squared minus 4ac. It has a name. Then if that's called the discriminant, by checking the discriminant, which is denoted by delta, which is nothing but b squared minus 4ac. See, discriminant is b squared minus 4ac. Simply by looking at the discriminant rather than going to the whole formula of quadratic equation, you can easily figure out whether there exist some kind of a solutions or not. Okay, how? If delta, this is called delta, this symbol delta, see, delta, this delta, delta, a Greek upper letter, delta, this one is delta, uppercase Greek letter to denote the discriminant, see, delta, delta. By looking at the delta, you can figure out whether we have a solutions or not. In another way, if delta is positive, we have 2 distinct solutions. If delta equals 0, we have one real solution. If delta is negative, we don't have a real solutions. We have a complex solutions, but we don't want to get into the complex solutions. So let's apply this to this formula. Here, this one in that form, you see, a is 1, that's the coefficient of x squared, b is negative 4, c is 5. You're going to compare, contrast, and figure out that which values would be for a, b, and c. Then we can calculate. Therefore, your discriminant we can calculate, b squared minus 4ac. Let's plug in the value, minus 4 squared minus 4 times a and 5. Let's keep going. 16, positive 16 minus 20, which is negative 4, see, less than 0, negative. Therefore, no real solutions. On the other hand, I can write some kind of a note here. If ax squared plus bx plus c equals 0, and if delta, which is b squared minus 4ac, is positive, two distinct real solutions, this one doesn't have a solution. How we know? If delta b squared minus 4ac is equal to 0, one coincident solution, just one solution, one real coincident. If delta, which is b squared minus 4ac, is negative, no real solutions, but have complex conjugate. They come like a pairs. Those are called conjugates. Complex number come like a pairs, complex conjugate. So this is under note. It's not related to our discussion, but this is for your knowledge. Okay. So let's get back to what we've been doing earlier. So we came up with the conclusion that there are no real solution. This implies is, you can put an arrow, that the given two graphs we can say like this, that the graphs of the given two functions do not intersect. They don't intersect. See, they don't intersect. What else we have to find in order to draw these two curves? We're simply gonna go ahead and find x-intercepts and y-intercept of these two graphs. Let's say you are interested in f of x squared minus 4x plus 10. In this one, and for this guy, I'm gonna find x-intercept, which is down the road we can say x-int. How do you find the x-int? In order to find the x-int, you're going to set y equals 0. See? Looks like they see, again you have to solve this equation. We came to a conclusion ahead of the time that this would not even come and get closer to whom? That's the next function, but that does not guarantee that this is not going to go through the x-axis. This is not going to meet the x-axis. That's not guaranteed. We can look at it. It looks like it's not factorable. Again, let's go to the discriminant. Delta b squared minus 4ac. B is nothing but minus 4 squared. 4. A is 1. C is 10. See? 16 minus 40, which is negative 4. See? Negative. That means no x-intercept. No x-intercept. No x-intercept. This. See, you can check the discriminant. You can check the discriminant. Good. Then let's go to the y-intercept. Y-int, in order to find the y-int, set x equals 0. X equals 0. X equals 0. See, that means x equals 0. F of 0 equals, see, 0 square is 0, this is 0, it's 10. So f0 is 10. Therefore, you can say y int is nothing but x coordinate is 0, y coordinate is 10. Sorry, 10. See, 0, 10. Let's pretty much do the same thing for the other function, g of x. G of x, 4x minus x squared. I'm going to go to x-intercepts, or x-int. Set g of x equals 0. That means 4x minus x squared equals 0. I can pull out x. See? So then you are left over with 4 minus x equals 0. Then x equals 0, or x minus 4 equals 0. Then x equals 0, or x equals 4. Therefore, x-ints are then 0, y is 0, 0, 0, or 4, 0. See? There are two x-intercepts for g of x. Then let's get into the y-intercept. To get y-intercept, set x equals 0. Then g0, 4x minus x squared, g0, 0 minus 0, g0 is 0, y-int definitely 0, 0, which is also equals to x-int. See, same thing. It's at the origin. This passes through origin g of x. See? Now let's draw these two. How could you gonna draw these two? Okay. On a xy plane. They are having discussion. I'm going to call this one y, this one x. You can remember, one's going to go through 0, 10, the other one going to go through 0, 0. In that sense, f of x goes through 0, 10, in that it's above g of x. See, looks like this one. When you draw, see, that's my f of x, which is x squared minus 4x plus 10. And this never going to meet this axis or this guy. See? This guy goes like that. This one, positive, open upward. This guy, g of x, 4x minus x squared. See, the leading coefficient is negative, therefore you have a open downward. In another way, you have a maximum. Here we have a minimum, see. And in addition to that one, see, this guy going to meet at 0, 0, and also at this point. See, this point is 0, 0. This point is, you can remember, 0, 4. Here, this point you can remember, 4, 0. This one 4, 0. This one 0, 10. To find this point, this is minimum point, min,